March 19, 1945. 50 miles off the coast of Honshu, Japan, the steel deck quivered beneath Lieutenant Commander Joseph T. Callahan's boots as he observed the flight crews readying the morning assault. The Catholic chaplain had been awake since 0400, conducting Mass for the early watch in the dimly illuminated wardroom. Now, as dawn broke across the Pacific horizon, he stood beside the island superstructure, watching ordnance crews secure the massive Tiny Tim rockets to the Corsair fighters. Each 11-foot rocket carried 500 pounds of high explosive, sufficient to pierce a battleship's armor. They had never been used in combat before. Franklin would be the first carrier to unleash them against the Japanese homeland. What Father O'Callahan could not know was that within 3 hours his ship would become a floating inferno, defying every forecast of destruction. USS Franklin would endure damage that naval engineers had calculated would send any carrier to the ocean floor within minutes. She would lose 87 men in an instant, more casualties than any other American warship would ever survive. Her flight deck would become a blazing hell of detonating rockets and ammunition, her hangar deck a furnace where temperatures climbed beyond 2002 Yet she would not sink. Against all logic of naval warfare and every principle of material science, she would endure, thanks to the innovations built into her very framework 5 years earlier by shipbuilders. Once told, their ideas were impossible. That morning had begun, with the familiar strain of combat operations near the Japanese coast. Task Force 58 had been pounding targets around Kyushu and Honshu for 3 consecutive days, softening defenses in advance of the April 1st Okinawa invasion. Franklin, part of Task Group 58.2 under Rear Admiral Ralph Davidson, had advanced closer to Japan than any other American carrier dared. At 50 miles from shore, she was well within range of land-based aircraft. Captain Leslie E. Garris, her commanding officer since November 1944, had driven his ship boldly forward. Some crewmen whispered that Garris, nicknamed Custer for his aggressive temperament, was taking reckless chances. But the mission demanded it. The closer Franklin operated, the more sorties her aircraft could fly, and the longer they could remain over target. Franklin launched her first strike at dawn. 12 Corsair fighters and 16 Avenger torpedo bombers roaring off the deck toward airfields around Kobe. The second strike was already staged, engines idling, propellers spinning, pilots running through last-minute checks. The deck was a symphony of controlled danger. Ordnance crews manhandled the experimental Tiny Tims into place, wrestling the enormous rockets onto wing mounts. Aviation fuel trucks had just topped off the tanks. Below, in the hangar deck, 22 more aircraft waited, 16 fully fueled, and 5 armed with bombs and rockets for the next launch. It was the most perilous moment in carrier operations. Hundreds of tons of aviation fuel and explosives exposed across 2 decks, where a single spark could unleash disaster. At 7:08 hours, a lone Yokosuka D-4Y Judy dive bomber appeared through a break in the clouds at 2,500 feet. The ship's radar failed to distinguish it amid the clutter of returning American aircraft. The combat air patrol, watching other directions, missed it. Anti-aircraft crews, tracking multiple contacts, had no time to respond before the Japanese pilot began his dive. His name would never be known. He had perhaps 30 seconds from the moment he nosed over until impact. In that half-minute, he dropped 2 550-pound, semi-armor-piercing bombs with deadly precision, then disappeared back into the clouds. The first bomb struck the E, flight deck, centerline 15 feet forward of the island structure. It tore through the 3-inch wooden planking, then through the steel deck beneath, and detonated in the hangar bay. The blast wave, traveling at nearly 26,000 feet per second, ripped through the packed aircraft like a colossal fist. Aviation fuel ignited instantly, producing a fireball that consumed everything within 50 feet. The explosion hurled the number 1 elevator, a 4-ton steel platform 60 feet long, straight out of its shaft like a missile. It shot 400 feet into the air, flipped end over end, and crashed back down in fragments that shredded planes and men alike. Secondary explosions rippled through the hangar as fuel tanks burst and ammunition cooked off. The second bomb exploded aft among the 31 aircraft poised for takeoff. It detonated on impact, igniting every fuel tank in sequence and sending a rolling wave of fire across the deck. Nearby ships felt the shock. Sailors were knocked off their feet on destroyers 1,000 yards away. On Franklin's flight deck, trapped pilots had little hope. Some unbuckled and leapt overboard, others burned in place, their screams lost in the roar of detonating munitions. What happened in the next 30 seconds would decide whether Franklin lived or died. In the hangar deck, where the first bomb had detonated, fires spread with terrifying speed. Gasoline from ruptured fuel tanks ran across the steel deck, seeking any opening. It found the ventilation ducts. Within seconds, burning gasoline vapor was being pumped throughout the ship by the ventilation system, still running on automatic. The heat ignited ready ammunition stored near the aircraft. 20-millimeter rounds began cooking off, their red traces streaking through the smoke like deadly fireflies. Shells exploded, with the force of grenades hurling shrapnel through the hangar. Men trying to reach firefighting equipment were cut down by their own ammunition, and then the tiny TIM rockets began to ignite. These massive weapons, each weighing 300 liters, were still experimental. No one knew how they would behave in a fire. The solid fuel motors were designed to burn at 5,000 degrees dF for 6 seconds, producing 50,000 kN of thrust. When the first one ignited at 7:11, minutes after the initial attack, its motor came to life with a shriek that could be heard over the roar of fire and explosion. The 11 FT missile shot across the deck horizontally like a meteor, trailing flame. It punched through the 0.5 in steel plating of the island structure as if it were tinfoil and exploded on the starboard side, showering the deck with molten metal and fragments. More followed. Rockets screamed in every direction, some plunging into the sea, others smashing through bulkheads, one cutting a gun crew in half before exploding in the water. Another rocketed the length of the flight deck and disappeared over the bow. The flight deck became a killing ground where men died from fire, explosion, or the random trajectories of weapons designed to destroy enemy ships. Lieutenant Commander Stephen Jurica Jr., the ship's navigator, was in his sea cabin just below the bridge when the first bomb hit. A 1930 Naval Academy graduate who had served as intelligence officer on USS Hornet during the Dittle raid, Jurica knew immediately what had happened. The distinctive double thump of bomb detonations followed by the rolling thunder of secondary explosions told the story. He grabbed his life jacket and battle helmet and ran for the bridge. What he saw when he emerged topside would haunt him for the rest of his life. The after two-thirds of the flight deck was a sea of flame. Aircraft were exploding, some launching themselves into the ocean as their engines caught fire and ran at full throttle, propellers screaming. The wooden deck planking was burning, adding to the inferno. Holes gaped where bombs and rockets had penetrated, some large enough to fall through. Men were on fire, running, rolling, jumping over the side. The list to starboard was already noticeable, perhaps 5 degrees and increasing. Black smoke boiled from the hangar deck openings, so thick it obscured the afterpart of the ship. And every few seconds, another tiny TIM rocket would ignite and scream across the deck on an unpredictable trajectory. Jurica began organizing damage control parties from stunned survivors. The forward section of the flight deck was still relatively clear. If they could create a fire break, if they could keep the flames from spreading forward, they might save the bow section. But the after-flight deck, where 31 aircraft had been spotted for launch, was beyond saving. Jerrica made one of the hardest decisions any officer ever makes. He ordered all personnel to abandon the after-flight deck, concentrate all efforts on saving the forward 2-3s of the ship. It meant leaving wounded men behind. It meant letting fires burn that might have been fought, but it meant focusing desperately limited resources where they might make a difference. In the engineering spaces 4 decks below, Lieutenant Junior Grade Donald Arthur Gary was standing his watch as engineering officer in the forward engine room when the bombs hit. A 1943 Naval Academy graduate, Gary had been aboard Franklin for less than 4 months. But those 4 months had included the October 30th, 1944 kamikaze attack that killed 56 men. At 800, 2 hours after the attack, Franklin's situation seemed hopeless to observers. She was dead in the water except for Pittsburgh's tow. She was listing 13 to starboard. Fire and smoke engulfed her from the island structure aft. Explosions continued as ammunition cooked off. The forward elevator, blown out of its shaft, lay twisted across the deck. The after elevator had been blown completely off the ship. Holes gaped in the flight deck some 20 ft across. Radio Tokyo, monitoring American communications, announced that a large American carrier had been sunk off Japan. Japanese submarines in the area received orders to find and finish off the wreck. Every man still aboard Franklin, every observer on the surrounding ships knew they were watching a death agony. Carriers didn't survive this kind of damage. Everyone knew that. But in the forward engine room, Donald Gary was achieving something extraordinary. Working with his engineering crew, breathing pressurized air in their sealed compartment, Gary had restored steam pressure to 2 of the forward boilers. He had 3 turbines operational. The electrical system, jury-rigged through emergency damage control cables, was providing power to critical systems throughout the forward part of the ship. At 0800, Gary reported to the bridge via sound-powered phone, the only communication system still working. Bridge forward engine room. I have steam on 2 boilers. 3 turbines operational. Can make turns for revolutions equivalent to 2 knots. 2 knots was almost nothing. Barely walking speed, but it was propulsion. Captain Garris, on receiving this report, made his most important decision. He ordered Pittsburgh to cast off the tow. Franklin would move under her own power. It was a decision that shocked everyone who witnessed it. A carrier dead in the water, burning, exploding continuously, couldn't possibly make way. The idea seemed insane, but Garras understood something fundamental. A ship that could move had a chance. A ship under tow was helpless. A ship under her own power could maneuver, could create airflow across the deck to blow smoke and heat away, could restore stability through speed and rudder control. At 0812, Franklin's massive bronze propellers began to turn. The engineering crew had managed to restore power to the starboard shafts. The ship, moving at barely 2 knots, began to inch away from the Japanese coast. It was one of the most remarkable moments in naval history. A carrier that should have sunk was moving under her own power. The restoration of propulsion transformed everything. Movement, even slow movement, created wind across the deck. The 25-knot winds generated by the ship's motion helped blow smoke and heat overboard instead of down into the ship. The improved airflow helped damage control parties operate. The list began to improve as the engineering crew carefully controlled counter-flooding, deliberately flooding port-side compartments to balance the thousands of tons of water that had accumulated on the starboard side from firefighting efforts. Most importantly, the fact that the ship could move gave the crew hope. Men who had been preparing to abandon ship returned to their stations. If Franklin could move, she could be saved. On the flight deck, Commander Jerrica and his damage control parties had erected a water curtain across the deck at frame 110, about 400 ft from the bow. Using every available fire hose, they created a barrier of spray between the forward section they had to save and the fires aft that they could not yet control. The water curtain, an innovation built into the Essex-class design, worked exactly as planned. The wall of spray absorbed radiant heat and knocked down smoke, creating a defensive line firefighters could hold. Behind that barrier, the forward flight deck remained relatively intact, but Franklin wasn't out of danger. At Aero 845, one of the worst secondary explosions occurred. A magazine filled with 5-in ammunition detonated below the hangar deck. The blast was catastrophic. Men on screening destroyers thought Franklin had finally blown up. A fireball rose 500 ft above the ship, a tower of flame and smoke visible for 20 balactuses. The explosion killed dozens of men who had been fighting fires in that section. It blew a hole through 3 decks from the hangar deck down to the 3rd deck. Fragments tore through spaces that had been undamaged, starting new fires, wounding more men. But something remarkable happened. The bulkheads around the magazine, all constructed of special treatment steel, contained most of the blast. In a conventionally built ship, the explosion would have torn through mild steel bulkheads and spread destruction laterally, probably breaking the ship's back. The fragments would have torn through adjacent spaces, detonating other magazines in a cascading catastrophe. But the STS bulkheads designed to resist fragmentation channeled the explosion upward and outward instead of sideways. The adjacent magazines remained intact. The fire mains running through that section were severed, but the redundant mains in other sections continued to supply pressure. The ship shuddered from the blast, but her structure held. By 1,002 hours and 52 minutes after the attack, Franklin had begun to stabilize. The fires were contained if not controlled. The list had been reduced to 9 degrees through careful counter-flooding. The engineering plant was delivering enough power for 4 knots, then 6, then 8. By noon, Franklin was making 15 knots. The transformation was stunning. A carrier that observers had watched dying was now moving at respectable speed. Her fires mostly controlled, her crew beginning to organize recovery operations. By 1600, 8 hours after the attack, the major fires were out. Smoke still poured from the wreckage, and small fires continued to flare as damage control parties found new pockets of burning material. But the Holocaust was over. Franklin had survived. The cost was staggering. According to the most recent research by naval historians, 87 men had been killed, most in the first 10 minutes. Another 487 were wounded, many with burns that would require months of treatment. More than 30% of her crew was dead or wounded. But she was afloat, she was moving, and she was heading for safety. Captain Garris pointed the bow southeast toward Ulithiatal 2,500 namimeters away. Franklin, escorted by Pittsburgh and screening destroyers, began the long journey home. Her top speed was initially 15 knots, though as the engineering crew made repairs and brought more boilers online, she would eventually achieve 25 knots. She could make it. The voyage to Ulithi tested every aspect of the design philosophy that Homer Lenoir Ferguson had championed 5 years earlier. Franklin was a floating wreck, barely seaworthy, listing with massive holes in her deck and hull, but she remained afloat because her structure held. The hangar deck, subjected to fires that had reached 2,000 degrees F, showed severe warping, but no catastrophic buckling. The beams supporting the deck had deformed from the heat, but had not failed. The flight deck, holed in 53 places, still supported the weight of damage control equipment and the hundreds of men working to make temporary repairs. The hull plating stressed by the list, the explosions, the counter-flooding maintained watertight integrity. Most remarkably, the underwater protection system designed to resist torpedo hits but subjected to enormous shock loads from internal explosions remained intact. Not a single critical bulkhead in the underwater protection system failed. Franklin reached Ulithi on March 24th, 6 days after the attack. She anchored in the lagoon, a floating morgue carrying 87 bodies. But she had arrived under her own power. Temporary repairs were made over 4 days, primarily patching the flight deck holes and making the after section of the ship weathertight for the transit to Pearl Harbor. On March 28th, Franklin departed Uli for Pearl Harbor. still capable of 20 knots despite her damage. She arrived at Pearl Harbor on April 3rd, causing a sensation. Word of her survival had spread through the Navy, but seeing the battered carrier enter the harbor under her own power was still stunning. The Navy made temporary repairs sufficient for the long transit through the Panama Canal and across to the Atlantic. On April 10th, Franklin departed Pearl Harbor under her own power, bound for the Brooklyn Navy Yard in New York. She arrived there on April 28, 1945, nearly 6 weeks after the attack. At Brooklyn, the full scale of the damage could finally be evaluated by Navy engineers and Bureau of Ships specialists. War Damage Report number 56, assembled over the following months, chronicled the devastation in detail. The hangar deck had been completely destroyed across nearly 40% of its surface. The flight deck was pierced in 53 locations, with holes ranging from 3 to 20 feet wide. Over 1/3 of the crew's berthing compartments were completely burned out. Steel bulkheads had been twisted by intense heat, everything inside reduced to ash. Thousands of structural components required replacement. The ventilation network needed total reconstruction, and the electrical system demanded major rebuilding. The damage was so extensive that restoration would have taken at least 2 years and cost nearly as much as constructing a new carrier. Yet the core framework remained intact. Naval architects inspecting the keel found it straight within tolerances. The hull plating retained its integrity despite the inferno. The engineering compartments, though affected by smoke and some warping from heat, were repairable. The internal framing and supports showed strain, but no fatal collapse. Franklin could have been restored. She never was, because the war ended before repairs commenced. But the fact that she could be rebuilt was remarkable in itself. The Navy made a different choice about Franklin's future. She stood as the most heavily damaged carrier to survive the war, a floating laboratory of combat endurance. Rather than begin immediate reconstruction, the Navy chose to use her as an experimental platform for studying how carriers survived catastrophic damage. For months, engineers crawled through her wreckage, measuring, photographing, and testing. They documented how special treatment steel, STS, performed under extreme heat, gauging deformation and mapping temperature gradients during the blaze. They analyzed how magazine explosions were contained by STS bulkheads and how redundant fire mains maintained pressure even when entire sections were destroyed. Every fragment of data was recorded, analyzed, and integrated into an extensive report that influenced every carrier design that followed. Yet Franklin's endurance wasn't the only validation of the Essex-class design. The class would prove its worth repeatedly in the closing months of the war. USS Bunker Hill, struck by 2 kamikaze aircraft on May 11, 1945, off Okinawa, endured damage that killed 396 men and wounded 264 more. The 2 attacks came just 30 seconds apart. The first suicide plane crashed into refueling aircraft on the flight deck, causing immense fires similar to Franklin's. The second hit penetrated to the gallery deck, spreading flames into the ship's interior. Bunker Hill's damage control crews fought the inferno for 5 hours before bringing it under control. She too survived and returned to port under her own power. Though never repaired for post-war duty, she didn't sink. USS Intrepid survived 4 separate kamikaze strikes during the war. Hit on October 29, 1944, repaired and returned. Hit again on November 25th, repaired again. Struck a 3rd time on March 18, 1945, and a 4th on April 16th. Each time her crew battled fires, made repairs, and resumed flight operations. She survived the war, serving until 1974 before being decommissioned after 31 years of service. Today, she stands as a museum ship in New York City. SS Enterprise, known as the Big E, became the most bombed, torpedoed, and otherwise battered aircraft carrier of World War II. to survive. Struck repeatedly, from the Eastern Solomons to Santa Cruz, and nearly destroyed by kamikazes in May 1945, her Essex-class structure and damage control systems saved her every time. USS Hancock. Below Wood, Lexington, Wasp, Ticonderoga, and Randolph all suffered severe battle damage and endured. The common denominator was the Essex-class blueprint, the extensive use of special treatment steel, comprehensive compartmentalization, redundant firefighting systems, and a structural philosophy that ensured every component contributed to survivability. None of these carriers sank. None were abandoned. All returned home. This wasn't fortune. It was engineering. The contrast with carriers of other navies was stark and well documented. British armored carriers, which many pre-war experts assumed would be more resilient than American designs, proved otherwise. Their 3-inch armored flight decks stopped bombs from piercing into the hangar, but when fires ignited within, they became nearly impossible to fight. The armor trapped heat and smoke, turning the hangar into an oven. Ventilation was insufficient. Firefighting crews couldn't operate effectively. Damage that an Essex-class carrier could repair in days sidelined British carriers for weeks. HMS Formidable was hit twice by kamikazes in 1945. Her armor held, but internal fires forced her withdrawal. HMS Illustrious was repeatedly knocked out by damage considered moderate by Essex-class standards. HMS Victorious and Indomitable suffered the same fate. Their design philosophy made them durable, but less adaptable and far more prone to mission kills. The Japanese carrier fleet, once the pride of the Pacific, suffered from treaty-era compromises and limited wartime experience. At Midway in June 1942, 4 Japanese fleet carriers, Akagi, Kaga, Soryu, and Hiryu, were sunk by bomb hits that an Essex-class carrier might have survived. Poor compartmentalization, primitive fire suppression, and minimal armor turned them into floating bombs. Once the chain explosions began, survival was impossible. By 1945, Japan had no operational fleet carriers left, while the United States had 20 Essex-class carriers dominating the Pacific. The statistics speak to Ferguson's vision with unforgiving clarity. 24 ships completed, 14 in combat during World War II. They were hit by bombs, torpedoes, and kamikazes 39 times. Across the class, over 2,600 men were killed, but not one ship was sunk or abandoned. Every damaged Essex-class carrier was repaired and restored to service, except Franklin and Bunker Hill, which remained in reserve because repairs were no longer urgent. Collectively, the class earned 143 battle stars and fought in every major Pacific campaign from Tarawa to Tokyo Bay. But who was the man behind this extraordinary design? Homer Lenoir Ferguson was born in Waynesville, North Carolina, on March 6, 1873. At age 15, he entered the U.S. Naval Academy at Annapolis, an unusually young midshipman even for that era. He graduated in 1892, reportedly first in his class, though some records suggest he finished third. Their records are ambiguous. What is clear is that he graduated with honors and was immediately selected for advanced study. Instead of going to sea, he was sent to Glasgow University in Scotland from 1892 to 1895 to study naval architecture and marine engineering under the renowned Scottish ship designers who were then leaders in the field. Glasgow in the 1890s was the center of the world shipbuilding industry. Scottish yards built the fastest, most advanced ships afloat. Ferguson studied under professors who had designed blockade runners for the Confederacy during the American Civil War. Fast ships that used iron frames and innovative hull designs. He learned stress analysis, hydrodynamics, metallurgy, and structural design. He absorbed the Scottish philosophy that ships should be built to survive, not just to be fast or heavily armed. A ship that sinks cannot complete its mission, his professors told him. Build ships that survive. Ferguson returned to the United States in 1895 and began a career as a naval constructor. He worked at the Columbian Iron Works in Baltimore, then at Navy yards in Portland, Oregon, Breton, Washington, and Bath, Maine. He supervised construction of battleships and cruisers, learning the practical realities of how ships were actually built versus how they were designed on paper. In 1902, he joined Newport News Shipbuilding, then a relatively small yard in Virginia that had been founded by railroad magnate Collis P. Huntington in 1886. Ferguson started as assistant superintendent of construction. His engineering skill and leadership ability were immediately apparent. In 1905, a Taj 32, Ferguson resigned from the Navy to become a full-time civilian employee at Newport News. He rose rapidly through the company. By 1914, he was vice president under President Albert Lloyd Hopkins. On May 7, 1915, Hopkins was traveling to England on shipyard business aboard RMS Lusitania when the liner was torpedoed by a German submarine off the Irish coast. Hopkins died when the ship sank, one of 1,198 victims. Ferguson, who had been expected to someday succeed Hopkins, was suddenly thrust into leadership. On July 22, 1915, at age 42, Homer Ferguson became president of Newport News Shipbuilding. He would hold that position for the next 31 years, through World War I, the Depression, and World War II. Ferguson's leadership transformed Newport News into America's premier naval shipyard. Under his direction, they had built 7 of the 16 battleships in Theodore Roosevelt's Great White Fleet that circumnavigated the globe in 1907 to 1909. During World War I, Ferguson oversaw emergency shipbuilding programs that delivered 25 destroyers to the Navy. He also pioneered worker welfare programs. In 1918, concerned about housing for shipyard workers, Ferguson worked with the federal government to create Hilton Village, one of America's first planned communities. He formalized the Newport News Apprentice School in 1919, creating a training program that became a national model for technical education. The Apprentice School still operates today, training the next generation of shipbuilders. But Ferguson's most important contribution came in the late 1930s as war clouds gathered over Europe and Asia. The Navy began planning a new generation of aircraft carriers to replace the treaty-limited designs of the 1920s. The Essex class, as it would be called, would be the backbone of America's carrier fleet. Ferguson saw an opportunity to revolutionize warship design. He had a radical idea: use armor as structure. Traditional naval architecture treated armor as dead weight. Protective plating added on top of the structural hull. Armor protected, but contributed nothing to strength. Ferguson argued the opposite. If you used special treatment steel throughout the ship, you could create a vessel where every plate contributed to both strength and protection. Special treatment steel had been developed by Carnegie Steel around 1910. It was a nickel-chrome steel alloy with remarkable properties. It had the protective qualities of Class B armor plate, capable of resisting fragmentation and providing significant protection against shell splinters and bomb fragments. But unlike traditional armor plate, STS was ductile enough to be fabricated as structural steel. It could be bent, welded, and formed into complex shapes. It could carry loads like structural steel. Most importantly, it could be used throughout a ship wherever strength was needed. The problem was cost. STS was vastly more expensive than mild structural steel, perhaps 30% more expensive, depending on thickness and specifications. Using STS throughout a carrier would drive the cost far above what the Navy wanted to pay. The Bureau of Ships initially rejected Ferguson's proposals as too expensive. Ferguson countered with detailed calculations. An Essex-class carrier using STS throughout would actually be lighter than a conventional design because the armor contributed to structural strength. That meant the ship could carry more aircraft, more fuel, more ammunition for the same displacement. More importantly, The structural redundancy created by using armor-grade steel everywhere meant that battle damage, which would a conventional carrier, might be survivable. You wouldn't save money on construction, Ferguson admitted, but you would save lives in combat, and you might save the ship. Ferguson had powerful allies. Officers who had studied the early carrier losses of the war understood that survivability mattered more than any other factor. Lexington, lost at the Battle of the Coral Sea in May 1942, had been destroyed not by the initial Japanese torpedo hits, but by vapor explosions from damaged fuel systems hours later. Yorktown, damaged at Coral Sea, had been patched up in just 48 hours at Pearl Harbor and sent back to fight at Midway. She survived multiple bomb and torpedo hits at Midway, was nearly saved by her crew, but succumbed to a submarine torpedo while under tow. Both carriers might have survived with better damage control systems and more robust structures. The Navy approved Ferguson's design with modifications. The hangar deck would be made of 2.5 in of special treatment, steel instead of the originally proposed 1.5 in. The fourth deck forming the bottom of the hangar box would be 1.5 in of STS. The flight deck would sit on a framework of STS I-beams. The armor belt protecting the waterline would use 4 in Class B armor plate backed by STS. Interior bulkheads throughout the ship would be STS where possible. The underwater protection system, the complex arrangement of compartments designed to absorb torpedo hits, would use thick STS bulkheads for the critical holding bulkhead that formed the final barrier against the sea. In total, each class carrier would use thousands of tons of special treatment steel. The exact figure varied by ship and is not clearly specified in unclassified documents, but engineering estimates suggested $3,000 to 4,000 tons per ship. The cost was enormous, but the result was a ship where every structural member contributed to survival. Ferguson pushed other innovations beyond just STS. The Essex class would have the most extensive compartmentalization of any carrier built to that time. Traditional carrier design used large open spaces for efficiency. Ferguson insisted on the opposite. Divide every space. Make every passageway a potential fire break. The Essex-class carriers were built with extensive compartmentalization throughout the ship with hundreds of separate compartments that could each be isolated, flooded or vented independently. The exact number of compartments is not specified in available sources, but the design philosophy was clear. You should be able to lose multiple adjacent compartments and still maintain buoyancy and stability. The firefighting system was revolutionary. Traditional carriers had a single fire main running the length of the ship. If the main was cut, entire sections lost firefighting capability. Ferguson designed a system of multiple independent fire mains, each fed by multiple pumps in different engine rooms, each capable of being cross-connected or isolated through a complex system of valves. The system used 9 separate fire pumps, each capable of delivering thousands of gallons per minute. If one section of the fire main was cut, flow could be rerouted through other sections. If pumps failed, other pumps could compensate. The hangar deck received an overhead sprinkler system that could deluge the entire space with seawater. Water curtains could be erected to create barriers against fire and smoke. The CO2 flooding system could pump carbon dioxide into fuel storage compartments to suppress fires. Emergency ventilation systems could pressurize spaces to keep smoke out, or vent spaces to remove smoke. Every aspect of the damage control system was designed with redundancy, with multiple backups, with the assumption that damage would occur and systems would fail. But the ship had to survive anyway. The first Essex-class carrier, USS Essex CV-9, was laid down on April 28, 1941 at Newport News Shipbuilding. Ferguson's Yard was the lead builder for the class. The ship was completed in just 20 months, being commissioned on December 31, 1942, Da USS. Yorktown CV-10, named to honor the carrier lost at Midway, was laid down at Newport News on December 1, 1941. Her keel was laid just 6 days before Pearl Harbor. She was commissioned on April 15, 1943, with Captain Joseph J. Clark commanding. USS Franklin CV-13 was laid down at Newport News on December 7, 1942. Exactly 1 year after Pearl Harbor. She was launched on October 14, 1943, sponsored by Lieutenant Commander Mildred H. McAfee, Director of the Waves Women's Naval Reserve. Franklin was commissioned on January 31, 1944. None of Ferguson's innovations had been proven in combat when the first Essex-class carriers steamed into the Pacific in 1943. They were theories, calculations, design choices made in drawing offices and shipyards far from battle. The ships looked impressive, but would they survive when tested? The answer came in battle after battle throughout 1943, 1944, and 1945. They survived. When hit by kamikazes that would have sunk earlier carriers, they remained afloat. When fires raged through their hangars, the damage control systems worked. When bombs penetrated their decks, the compartmentalization contained the damage. The Essex class became the most successful aircraft carrier design in history, precisely because Homer Ferguson had insisted on building ships that could survive. Ferguson remained president of Newport News Shipbuilding until July 31, 1946. He retired at age 73, having seen his carriers survive every test combat could impose. After retirement, he remained active in the Newport News community. He was instrumental in founding the Mariners Museum in Newport News, along with Anna Hyatt Huntington and her husband Archer. Monsieur Huntington. Ferguson served on the museum's board and helped build its collections, documenting the history of shipbuilding and maritime commerce. He died on March 14, 1953, just a week after his 80th birthday. He received no Medal of Honor, no Navy Cross, no congressional recognition for his contributions to the war effort. His name appears on no ships. The general public never knew who he was. His contribution was too technical, too abstract, too far removed from the drama of battle to capture popular imagination. But the men who survived Franklin never forgot. In the decades after the war, Franklin's survivors organized reunions. The first reunion was held in 1947 in New York City. About 200 men attended. They shared stories, remembered the dead, and marveled at their own survival. The reunions continued annually for many years, then every few years as the survivors aged. The gatherings grew smaller as men died, but the bonds remained strong. In 1995, on the 50th anniversary of the attack, about 80 survivors gathered in Charleston, South Carolina. They visited the USS Yorktown Museum ship, an Essex-class carrier like Franklin, walking the decks of a sister ship, seeing the compartments, the fire mains, the structural details. They understood more deeply how they had survived. The engineering was visible in ways it had never been when they served aboard Franklin. The STS bulkheads, the multiple fire mains, the compartmentalization, all the design choices that had saved them became tangible. In 2005, 60 years after the attack, fewer than 30 survivors attended what would be the last official reunion. Thamet in Norfolk, Virginia, just a few miles from the Newport News shipyard where their ship had been built. The shipyard arranged a tour for them. These men, now in their 80s, walked through the yard where nuclear carriers were being built. They saw computer-aided design stations, robotic welding equipment, advanced materials. But their philosophy remained the same: build ships that survive. The young shipbuilders working on modern carriers were continuing the tradition Homer Ferguson had established. The survivors told the young workers a simple message: we're alive because men like you built our ship right. Build these ships right, too. Someday, men you'll never meet will owe you their lives. It was the fundamental truth of their experience. Engineering excellence translated directly into saved lives. Every man who walked off Franklin alive owed his survival to decisions made in drawing offices and fabrication shops years before the war. Decisions about steel thickness, bulkhead placement, fire main routing, compartment design. The chaplain who fought fires, the engineer who kept the engines running, the navigator who organized damage control, all were enabled by the ship beneath their feet. Without Ferguson's innovations, their courage would have been futile. Franklin would have sunk, and 800 men would have become 2,500 dead. The individual stories of Franklin's Medal of Honor recipients illustrate the human dimension of the ship's survival. Lieutenant Commander Joseph Timothy O'Callaghan received the Medal of Honor, the only chaplain in naval history to be so honored. His citation reads in part, "Lieutenant Commander O'Callaghan courageously led officers and men in fighting the fires and combating the damage. He braved dangerous and burning compartments, areas alive with exploding ammunition and threatened by flames to lead parties below and save lives. His stout heart, great courage, and cool leadership were the rallying point of the crew." After the war, O'Callaghan returned to teaching at Holy Cross College in Worcester, Massachusetts. He taught mathematics and physics, served as head of the physics department, and rarely spoke publicly about his Medal of Honor. He died in 1964 at age 62. His autobiography, I Wash a Plane on the Franklin, published in 1956, remains one of the finest accounts of the attack. Lieutenant Junior Grade Donald Arthur Gary received the Medal of Honor for his actions in the engineering spaces. His citation notes that he organized handled firefighting parties to the hangar deck and entered the No. 3 fire room to raise steam in one boiler. His prompt actions in risking his life to help save his ship were of great value in helping to prevent the loss of Thiepsel. The citation specifically identifies him as Lieutenant Junior Grade and notes his role in maintaining engineering power. After the war, Gary left the Navy and returned to civilian life in Ohio. He worked as an engineer for Ohio Edison, a power company, until his retirement in 1960. He received a letter from a young naval officer asking for advice about damage control procedures. Gary wrote back with detailed technical instructions and added, "Remember that systems don't fail. People fail. If you've designed your systems with enough redundancy, with enough backup, with enough alternative paths, then when people are at their limit, exhausted and terrified and ready to quit, the ship will carry them. Build that kind of ship." Gary died in 1977 at age 56. Commander Stephen Jerrica Jr., the navigator who organized flight deck damage control efforts, received the Navy Cross. After the war, he continued his naval career, eventually retiring as a captain. His experiences on Franklin informed his later work in damage control training. He died in 1993 at age 83. Captain Leslie E. Gerace remained a controversial figure. His strict discipline and autocratic command style had made him unpopular with many crew members before the attack. After the attack, he faced allegations that he had accused men who abandoned ship of desertion, despite the fact that many had been ordered to abandon ship or had jumped overboard to escape certain death from fire. A Navy investigation found no wrongdoing, concluding that in the chaos of the disaster, communications had broken down, and some men had genuinely believed abandoned ship had been ordered, while others had jumped to save themselves. Gerace was promoted to Rear Admiral after the war, but the controversy followed him. He retired in 1946 and died in 1975, largely forgotten by the public. But naval historians studying Franklin's survival noted that his decision to keep the ship moving, to refuse to give up, to drive his crew beyond normal limits, was validated by Franklin's survival. Without both the engineering capability to survive and the command determination to save the ship, Franklin would have been lost. Franklin's post-war fate was inglorious compared to her wartime service. After arriving in Brooklyn in April 1945, she remained there for the duration of the war. Japan surrendered in August 1945 before repairs could begin. The Navy decided that with the war over and no immediate need for her, the massive repair costs couldn't be justified. Franklin was decommissioned on February 17, 1947, and placed in the reserve fleet at Bayonne, New Jersey. She remained in reserve for nearly 20 years, a ghost ship slowly deteriorating. The Navy Red designated her CVA-13 attack carrier in 1952, then CVS-13 anti-submarine carrier in 1959, and finally AVT-8 aircraft transport in 1961-1963. These were paper changes. Franklin never left the reserve fleet. She was too heavily damaged, and the cost of the extensive modernization necessary to make her useful for post-war operations was deemed unjustifiable when newer carriers were available. In 1964, Franklin was struck from the Naval Vessel Register. In May 1966, she was sold for scrapping to Peak Iron and Metal Company in Portsmouth, Virginia, for $228,000. However, the Navy repossessed her in June 1966 because of an urgent Bureau of Ships requirement for her 4 turbogenerators, which were needed for other ships. Finally, on July 27, 1966, she was sold again to Portsmouth Salvage Company in Chesapeake, Virginia, for scrap. On August 1, 1966, tugs began towing Franklin from her berth in the reserve fleet for the last time. As she moved down the channel toward the scrapyard, a Coast Guard cutter passed by, rendering honors with 3 short blasts of its whistle, a naval tradition for showing respect. The cutter's captain, a World War II veteran, later explained his decision. "That ship earned honors. I didn't care what orders said. She deserved respect." It was the last salute Franklin received. Franklin was cut up for scrap over the following months. Her steel, including the thousands of tons of special treatment steel that had saved her, was recycled into new construction. Some of that steel, according to Navy legend, though not officially confirmed, went into the construction of USS Enterprise CVN-65, the first nuclear-powered aircraft carrier commissioned in 1961. The Enterprise served for 51 years, the longest service life of any aircraft carrier in history. When she was finally inactivated in 2012, naval historians noted that her survivability features, her extensive compartmentalization and redundant systems, traced their lineage directly back to the Essex-class design principles. The ship that refused to die had taught the Navy how to build ships that wouldn't need to prove their toughness the way Franklin had. Today, at the Naval History and Heritage Command in Washington, D.C., researchers can examine War Damage Report Number 56, the official analysis of Franklin's damage and survival. The document, over 300 pages of technical analysis, photographs, and diagrams, remains classified as restricted, not because it contains information about modern carriers, but because the damage control techniques it describes remain so effective that the Navy considers them operationally sensitive. Every damage control school in the Navy uses Franklin's survival as a case study. Every naval architect designing combat ships studies how her structure held together under impossible conditions. Every officer planning carrier operations understands that their confidence in taking risks, in operating close to enemy shores, in pressing attacks home rests on knowledge that their ship is designed to survive. The broader message of Franklin's saga reaches far beyond naval combat. In every domain where human lives rely on engineering, the same fundamentals hold true. Designed for the worst imaginable conditions, built with redundancy, use the highest quality materials available, even when they demand greater cost. Create systems that don't collapse suddenly, that fail gradually, giving people precious time to respond and recover. Homer Ferguson applied these ideas to aircraft carriers in 1940. They applied just as directly to airplanes, spacecraft, skyscrapers in seismic zones, to any human creation where failure equals death. The assault on Franklin claimed 87 lives in half an hour. The ship's endurance saved roughly 100 others. That proportion, more than 2 lives preserved for every one lost, embodies the true dividend of superior design. The costly steel, the additional compartments, the backup systems, all demanded time, money, and effort during construction. Yet they purchased 1,700 lives in wartime. No one can truly measure what those men gave back to the world afterward. The families they raised, the companies they built, the students they taught, the lives they influenced. The echoes of their survival stretch across generations, impossible to count, but undeniably real. Franklin's account is, in the end, about the unseen victory, the triumph achieved before the battle, in drawing rooms and shipyards, where designers and builders make choices that decide whether men will live or die years later. These choices lack the spectacle of battle. No one receives a medal for specifying thicker armor plate. No one earns fame for demanding redundant firefighting systems. Yet these decisions matter as deeply as bravery under fire, perhaps even more, because they make courage effective. Homer. Ferguson never earned a Medal of Honor for crafting ships that preserved thousands of lives. He never appeared in newsreels or schoolbooks as a hero. His legacy was too technical, too distant, too far removed from the chaos and smoke of war. But the crew of Franklin knew. The 1,700 men who escaped that blazing vessel alive, who returned to their loved ones, who lived long, ordinary lives because their ship refused to die. They knew that somewhere along the chain of design and construction, someone had chosen wisely. Someone had insisted on stronger steel, extra bulkheads, and backup systems. Someone had believed human life was worth the additional cost. And on March 19, 1945, off Japan's coast, those decisions proved worth more than all the valor, sacrifice, and heroism combined. Because bravery without tools becomes martyrdom. Sacrifice without capability becomes loss. Heroism without support becomes tragedy. But when courageous men sail ships conceived by skillful engineers, when sacrifice is strengthened by design and heroism is reinforced by preparation, then victory becomes possible. Franklin proved this truth at terrible cost, then brought 1,700 witnesses home to affirm it. The ship that should have perished instead demonstrated that survival was achievable, and in doing so, vindicated every decision that went into her creation.